Hello, this is section 5.5, graphs of relations and functions. Okay, so the domain of a function is the set of values of the independent variable, which we often call the x values. The range of a function is a set of values of the dependent variable, which we often call our y values. Points are only connected on a graph if that variable is considered to be continuous. For example, time, height, and temperature are considered to be continuous because values exist between the whole numbers. For example, you could say it's not just happening to be 1 o'clock or 2 o'clock, you could say it's 1:30 or 1:35. To grow between being 5 feet tall and 6 feet tall, you hit all of the other heights in between. So those are continuous. If it's not continuous, we would call it discrete. And that would mean that we would not connect the points. Okay, so the key here is, when are we going to connect the points? And when are we going to not connect the points? So they're connected if they're continuous. Okay, and if they're discrete, they're not connected. So we have to think about each particular example and whether or not we should connect the points. So here I've got two graphs, and I want to ask which of the following two examples represents a function. Now remember, we studied what a function was in a previous section. I can't remember if it was 5.1 or 5.2 because it's been a while now. But what we're looking for is, do we have the same x coordinate going to more than one y coordinate? And as we can see here, those 3 points that have an x coordinate of 1, it has a y coordinate of 3, then we have the point 1, 4, then we have the point 1, 5. So because of that, this is not a function. Now over here, there's no place where we have the same x coordinate going to more than one y coordinate. In other words, we don't have the same input going to more than one output. And so this one is actually, yes, a function. Now there's a very simple way that we can test whether or not something is called a function. And we call it a vertical line test. And you can literally take your pencil. Let's see if I can find a quick picture of a pencil here to demonstrate this. Probably can. Oh my gosh. Pencil. Are you kidding? No picture of a pencil. Never mind. I'll just draw a big fat line and we'll pretend that it's a pencil. Okay, so let's pretend that that's our pencil. If you hold your pencil this way on the page, not this way, but straight up and down, which we call vertical, and then you roll it across your graph, you can ask if it hits more than one spot at the same time. So for example, this one's a function because as I scan my pencil across using the vertical line test, it only ever hits the graph at one point at a time. Okay, if I do that over here, there's a problem there. I've hit 3 points at the same time. So that means that that is not a function. So that's a really quick way you can do it. You can do it using your own pencil, which is really simple, or whatever you're holding. And so we can say in conclusion that a graph represents a function when no 2 points on the graph lie on the same vertical line. Now it's okay if we have them lying on the same horizontal line, but not the same vertical line. So we call that the vertical line test. I'm just going to put the quotes marks here. So that's a really common test used in mathematics to figure out if something is a function or not. So I'd say that's a really important point. Okay, going on to example 1. Do these graphs represent a function or not? So I'm going to bring out my trusty little pencil here, and I'm going to scan it over this first graph and see if it ever hits more than 1 point at the same time. No, just 1, 1, 1, 1, 1. So that one is okay. So yes, that is a function. So I'm going to go ahead and write that here. Now, if I try my vertical line test on the second graph, I'm okay after the first point, but as soon as I get to these second points, I'm covering more than 2 points at the same time. There's a problem there. There's a problem there. Okay, so this one is definitely not a function. Okay, moving on to the next page here. So now we're going to determine the domain and the range of the graphs of functions. So both of these are already known to be functions. They would both pass my vertical line test. And so what I want to do here is show what I mean by domain and range, and then also show how we write that out mathematically. So I'm going to switch back to my pen, and the domain is how far the graph goes left to right. And the range is how far the graph goes on the y-axis, which is up and down. And if you know anything about music, you would say that the range of your voice is from the lowest note to the highest note. So it's the same kind of concept here, mathematically speaking. So domain is written because there's quite a few values as we go from here all the way to here. It's hitting all these numbers in between, including the decimals and the fractions. So we can't list every number because there's an infinite number of points. So what we have to do is give a range of x values. And the way that we're going to say that, or the way that we're going to write that, is like this. So we know that we started at -6 widthwise and we ended at +5. And so we put the lowest number on the left, that's the -6. We put our highest number on the right, and we put our x in the middle, and then we use our less than or equal to symbols in between. Now this works because this is a triple statement, but if I cover up any part of the statement, I'll just show you what I mean by covering it up with a little rectangle here. Oh, there, an orange rectangle. Let's do that. So if I cover up that part, that statement is true that -6 is less than or equal to x, or you can read it backwards, x is greater than or equal to -6. It's also true when I read it this way, x is less than or equal to -5. That's also true. And it's also true when I cover up the middle part, it is true that -6 is less than or equal to 5. So this is a good way to write out our domain and our range. It's basically saying, hey, there's a whole series of numbers in here that works. Now we're going to do the same thing for the range, except when we're talking about the range, we're now talking about how low on the y-axis did it go to how high on the y-axis did it go. So the domain is the set of all real numbers starting at -4, and x is going all the way up to 2. Now, I might not have mentioned this yet, but the curly brackets here is called set notation, and that's the way that we say there's a number of answers that fit the domain and range. Okay, so let's do the same thing over here. So this time the domain would be going from here all the way to here, and the range will be going, well, I guess maybe I should start the smallest from here all the way up to here. So the domain, pardon me, is always the across part. So that went from -3 all the way up to 5. And the range goes from 3 all the way up to 7. Okay, so that is how you write out the domain and range of a function. We're going to skip example 3 for right now. You can always look on the textbook and read the example on page 292. So that might be a helpful example when you're working on your homework. And there's a digital link to the digital copy of the textbook on the Google Classroom. So you can check that out. Example 4, let's skip to that one. So that's determining the domain values and range values from the graph of a function. So here's a graph of the function g of x equals 4x minus 3. Determine the range value when the domain value is 3. So I'm going to cheat here a little bit and put in a note that the range is asking me for the y value and the domain means the x value. So what they're saying is when x equals 3, what is y? So we're going to go to our graph and count over on the x-axis. See, this is the x-axis. It's the horizontal axis. We're going to count over to 3, and then we're going to read up here and see what that number is on our y-axis. So if I can estimate here, that looks like it's about halfway between 8 and whatever this block is. Now we're counting up by 2, so this would actually be 10. So halfway between 8 and 10 would be 9. If we do the other question, this one's asking for the domain value. So it's asking us, hey, what's the x value when y is equal to -7? So if I go down to y is equal to -7, well, this would be -6. So here's -7. If I read across to my line and then go up, the question is, where am I here? So I'm halfway between 0 and -2. So I'm actually at -1. Now there actually is a neat thing we can do here, which is we can check our answers. So we know that 3 and 9 were together on the first question, and that means that's an ordered pair, 3, 9. We always write the x first and then the y. And we can check this in our function that was given. So I'm going to write y equals 4x minus 3. Remember, g of x is just a fancy way of saying y. It's just a function notation. So I'm going to put my 9 in for the y, and I'm going to substitute in 3 for the x, and just check to see if I get an answer that makes sense. So 4 times 3 is 12. 12 minus 3 is 9. So I indeed do get that 9 equals 9. Now you might say, well, why do I need to check? It was pretty obvious what my answer was from looking at the graph. I suppose the reason is that we did have to do a little bit of estimating when we were looking on our graph. We were assuming, for example, that parts of the graph were exactly halfway in between some indicated scales. So we do have to be a little bit careful there. Our next point is -1, -7. Careful, make sure you write the x value first. So it's the same equation, y equals 4x minus 3. In the spot of the y, I'm going to put the -7. In the spot of the x, I'm going to put the -1. Remember, BEDMAS, we have to multiply first. So on the left, we have -7 equals -4 minus 3. And then -4 minus 3 is -7. So I know that I did come up with the 2 right answers here because I checked my work by plugging into the equation. Okay, so that is the notes for section 5.5. So you should be able to now work on the assignment for 5.5. And again, that's listed on the homework list, and the assignment is from the textbook. Okay, thanks for tuning into this video, everybody, and we will see you next time.